This video is going to discuss the determination of the standard Gibbs free energy for this reaction. Ammonium nitrate as a solid going to three, different types of gases, and really a total of 7 gas molecules. 2 here, nitrogen, 1 here, and 4 water molecules. So as you might expect, this is a very explosive reaction. One solid, ammonium nitrate, giving you basically 7 different types of gases coming off, or a total of 7 molecules of gas coming off. So I thought I'm from West Texas, and those who lived in West, Texas remember an explosion of the ammonium nitrate fertilizer plant right next to the railroad tracks, and just across from those railroad tracks our boys played football and played soccer. So that field was totally leveled, and the train tracks were thrown up on top of it. It was just a mess. And we live 20 miles south of the city proper. West is not a big city, but it's just a town. And we saw the light from it. And if you were in the trajectory, we were a little bit low, but you could actually feel the wind and hear this sonic boom. If you were in this town, it knocked you off your feet. If you were out of town and you're a little bit higher, you heard it and saw the light. So anyway, let's work on finding just how spontaneous this reaction is at 25 degrees Celsius. Now, all that said, please know that, of course, once it gets started, it's not going to stay at 25 degrees Celsius. And I think that actually drives the reaction even faster, because the entropy values we're going to see, they're going to start going up pretty quick for your gases typically. These are at standard temperature and pressure, 1 atmosphere and 298 degrees Kelvin, but these might change a lot at a different temperature. Let's just see what it would be at 25 degrees Celsius, the standard Gibbs energy for this reaction. So the first thing you have to do, if they give you a table of enthalpy values and entropy values, you're going to use this in the standard Gibbs free energy equation to take the sum of all the delta H's, products minus reagent, and the sum of the entropy values, the change in that from products minus reagent. So let's do the enthalpy of reaction first. Now this is not enthalpy of formation. Please, this is enthalpy of this reaction. So there's a big difference here. We're going to use the enthalpy of formation values for each of these to determine the enthalpy of this reaction, the enthalpy change for this reaction. So let's go ahead and think of products. We're going to do that side first, put them in here, and then have subtracted from that the enthalpy of formation for ammonium nitrate. So the first two we can get out of the way is the nitrogen and the oxygen. Enthalpy of formation, we know, is for the formation of whatever we're talking about from the elements. Well, these are already the elements, so that's going to be 0. So of course 0 times 2 is 0, and 0 times 1 is 0. So we don't have to worry about that. But we do have the 4 as a coefficient. It's the number of moles of water made, and we know for water that the enthalpy of formation is minus 241.8. And I forgot to put the legends here, what this represents. This is water, this is our oxygen, this is nitrogen, and this is the solid, the ammonium nitrate. So I don't have enough room there. So we're going to take 4 times the minus 241.8, and I'm leaving units out, but these would be in kilojoules per mole, but this is 4 moles, so 4 moles times 241.8 kilojoules per mole, so the moles would drop out. Now that's our product, but we know we sum all the products up, but we have to subtract the reagents heats of formation, and so that would be the minus 2 times the minus 365.6, because that's the only reagent we have. And that's our equation for finding the enthalpy, standard enthalpy of this reaction from the standard enthalpy of formation for those reagents and products. So I'm going to bring out the calculator here and see what we get. I'm going to just go ahead and use positive here. This is going to be this is a negative and that's a positive, but I'm just finding the difference here. 4 times the 241.8 equals, and we'll subtract 2 times 365.6 equals, and I get here now a negative 236, and we're just going to say kilojoules because we got rid of the mole values, the mole term, by using the coefficients. So that's our first term we need for this delta H. Let's go get the delta S. Now we're using not delta S's as our starting point. It's just this entropy of the solid is 151.1. Now I'm a little suspicious about this number. This is the hardest one to find, the entropy, standard entropy for ammonium nitrate solid. You'd expect that solids typically have a lower entropy than the gases. They don't have as many modes of motion to put their energy into or whatever, but maybe because it's so many elements in it that has different ways in which it hides that energy, so to speak, or spreads it out in the vibrational modes or whatever. The gases are all pretty similar as far as their entropy. So this one's I'm a little bit suspicious of, but let's use it and see what happens. And entropy values typically don't have as much of an impact on this equation as the enthalpy values do. So now let's turn to blue. So entropy, and we're finding the standard enthalpy change, so we're still going to do sort of our products minus our reagents. So we're going to have a few more numbers here and a few more calculations to consider, so I'm going to go a little bit small. So the nitrogen first is 2 times 191.6 plus the oxygen. We only have one of those, but its entropy value is 205.2 plus, now we have 4 of these, 4 times that 188.8, and it looks like it just barely made it. So these 3, we're going to add them all up, and we'll get our combined value, positive value, but we're going to subtract off of it the entropy for the solid, and it's 2 times that. 2 times 1, since there's 2, we have to use 2 up front. 2 times the 151.1. So one thing to point out here is you can kind of see when you start to make more stuff, you have more ways in which the energy can be delocalized, dispersed, spread out, diffused, or whatever word you want to use. This is going to be the high entropy side, and that's usually the case when you have a lot of stuff versus a few stuff, or the same, actually, and even worse, the same stuff. So when you get a lot of different particles, they all carry a significant amount of entropy with them. So this is going to be a lot larger than this here. So let's see how much larger. So just adding all these up. 4 times that 188.8 equals, yeah, pretty significant, 1,343.6, and this is in joules, so I want to remember that because I'm going to have to convert that to kilojoules, minus 302.2 joules. So I'm going to go ahead and just write that in over here, what we're going to have as a final number. Sorry for the delay. We still are in the thousands. 1,041.4. Now I'm going to change that to kilojoules. So to do that, this is a lot of joules, but we're going to move the decimal point over 3 places before we plug it into our equation. So let's go ahead and get ready to plug it in. So R delta G, standard Gibbs free energy, is equal to that minus 236 kilojoules minus 298. You say, where'd you get the 298? remember, we're at standard conditions, so the temperature is always 298 or 25 degrees Celsius. And now we can bring in that value here, but we're going to convert it to, again, kilojoules. So we're going to say 1.041 kilojoules. I'll just go ahead and use red to know that we signify that we have the same same units. And it really still is over T, because we have the Kelvin here, it's still over Kelvin here, but that would cancel out the kelvins with kelvins. So we're going to end up with just kilojoules and kilojoules added together. But you can kind of tell that we're going to have a pretty significant contribution by entropy. 298 times 1 is going to give you something around 298. So let's do the whole math. But this, just realize this term is helping us. It's going to give us an overall negative, and we already have a huge negative. This is explosive stuff. Very high amount of Gibbs free energy. Very high change in entropy. 298 times that 1.04. 1 equals 310.2. Now I'm just going to go ahead and add it to the 236. That's 236 equals, we get a final, I'm going to just put it in black, and it's going to be negative because this was a negative, this was negative. I just added it up, keeping it positive. It's a minus 546.2 kilojoules as Gibbs, standard Gibbs free energy for this reaction. I don't want to say per mole, because for this whole reaction, we have this much in terms of free energy, standard Gibbs free energy. We have this much. That is a lot. This is certainly explosive, and I don't want to, just respect chemistry. We lost friends that we knew, thankfully, at least firefighters, but yeah. Dangerous stuff, ammonium nitrate, as we've seen in the last few years. Beirut had their, I guess, fill of disaster with ammonium nitrate. That's calculation of the standard Gibbs free energy of the reaction of ammonium nitrate solid to make nitrogen gas, oxygen gas, and water. And this happens typically at a high temperature. It feeds itself, and it's a runaway reaction. Bye-bye.